Time for the middle part of the Proterozoic Eon, the Mesoproterozoic Era. This one is really all about the coming together of cratons to form another supercontinent called Rodinia. And we have rocks in Arizona that represent this event. In the Grand Canyon, we have Mesoproterozoic rocks, like here at Hance Rapid, rocks of the Grand Canyon supergroup along the river. And also life forms. We're going to see a little change in the types of life, but it's really the heyday of stromatolites. And these stromatolitic domes here from the Bass Formation in the Grand Canyon represent that. Mesoproterozoic era stretches from 1600 to 1000 million. So about 600 million years of geologic time. Again, here's the excerpt from the official ICS timescale. And this middle part of the Proterozoic has 3 periods that are officially recognized. And as with the Paleoproterozoic, we're not really going to be concerning ourselves with these specific period names. Well, the geography of the Mesoproterozoic really starts with a supercontinent and ends with a supercontinent. So if you remember from the Paleoproterozoic, Columbia was the supercontinent that had formed, and it is still coherent at the beginning of the Mesoproterozoic. And then at about 1500 million, it starts to rift apart, and the separate cratons go their various ways for a while and then come back together by the end of the era. By about 1100, we start getting continents coming together, and certainly by 1000, we have what we now call the supercontinent Rodinia. Rodinia was a large landmass, being a supercontinent, and Laurentia was an integral part of it. And regardless of the exact orientation, north, south, east, and west, we can think about what the geography was. And so in the western, what is more or less now the western part of Laurentia, we can make a map. This is from Dr. Ron Blakey's work. He is professor emeritus at NAU, and he compiled all sorts of different geological studies into a series of paleogeographic maps. And this one's for the Mesoproterozoic, and it shows pretty much the Laurentian craton on the right, Arizona and Utah and everything east. And then there was a land mass basically continued off to the west, and that part of Rodinia is now East Antarctica and Australia. And everything was together, and what the theory is the southwest U.S., East Antarctica, and Australia were once together, and this is called the sweat hypothesis. Okay, so basically you could walk from Yuma to the west, and there was no Pacific Ocean at the time. It was basically all continent. The continents, the cratons that were there, what is now Australia and East Antarctica. So let's talk about the tectonics of the Mesoproterozoic. And really it's about the rifting, coming together eventually of cratons. And so Columbia was the supercontinent at the beginning of the era. And soon thereafter, between about 1500 and 1400 million, it started to break up and the various pieces started to rift apart. Okay, and so this shows the distribution of the different cratons at the time. And you can see Laurentia here, kind of centered on the equator, was a major part of it, with Baltica to the south and Amazonia and some of the African cratons, Chinese cratons, etc. A large ocean off to the west. This was Columbia, and it rifted apart. This line right here is a subduction zone. So the timing on this was sometime during the early part of the Mesoproterozoic. So another name for Columbia was Nuna. And you might see that too, but I use Columbia as the name. Okay, so time passed and eventually Rodinia assembled. Maybe as early as 1300 down to about 1100 is when we think it came together. Staying together for a few hundred million years, about 750. So this one again included pretty much all the major pieces. including Laurentia, Australia, Antarctica, Amazonia, and others. And again, Laurentia was straddling the equator here, and it was kind of in the middle. It's kind of the core of Rodinia. And so again, here's where you can see Laurentia, and off to it, the one side here are East Antarctica and Australia. The green areas here are mountain belts that were formed as everything came together. So it says 1.1 GA, or 1100 million year old mountain belts that were created as these cratons came together and collided. And if you're counting, this is number 5 or so. If we start with Valbara, Kenorland, Columbia, and now Rodinia. And so we're getting towards the end here, number 5, and we have 2 more to go. But Rodinia was a major supercontinent, and it basically assembled by the end of the Mesoproterozoic. Well, as Rodinia came together, there were a number of different orogenies around its margins that were caused by the collision of various cratonic blocks. And one of the ones that's relevant for Laurentia is the Grenville orogeny. And we think it started about 1250. So that represents basically the first collision of Laurentia with other cratons. And it lasted until about 980. Okay, and so through most of the rest of the Mesoproterozoic. Again, this orogeny represents the collision and suturing, or coming together, accretion, joining of Laurentia and other continental masses. Okay, and so we think that this is the mountain belt itself, the Grenville origin or mountain belt, and it has different names in different countries. Basically, when you put it all back together, it's one big mountain belt. And on this map, it's right here. North America, or Laurentia, coming together with some of these other southern cratons, form this mountain belt. Okay, and so the Grenville orogeny was a major one, and it represents the assembly of the supercontinent Rodinia. Okay, let's talk about some of the rocks of the Mesoproterozoic, starting with our own home supercraton Laurentia, the Belt Purcell supergroup, which is a collection of a whole bunch of different rock formations that have an age of about 1470 to 1400. And these are located in the northwest part of the United States and on into Canada. So the Belt supergroup is mostly Montana and Idaho, and the Purcell supergroup is more or less the continuation into Canada. And what these represent are lake sediments or shallow marine sediments, combination of the two. A word for lake that you might see quite often is a lacustrine, and so it just means lake related. So you've probably seen pictures of the Belt Purcell supergroup because some fantastic scenery is included in places like Glacier National Park. All these rocks here, these are all, you can see the layers of this, and so those are nice sedimentary layers of the Belt Purcell supergroup. Okay, and here's a geologic cross section showing basically some of the different layers. And there's sediments mostly, but there are also some intrusions as well. A beautiful glaciated scenery. The rocks themselves are very old, Mesoproterozoic. The landscape, though, is much younger. The glaciation happened just in the last few 100,000 years. Well, anorogenic granites are another major rock type of the Mesoproterozoic. Anorogenic means not orogenic, and so and you put an in front of any word, it means, not. So it was originally thought these weren't related to any kind of tectonic event, and that's being worked out right now. But these have an age that are similar to the Belt Purcell, about 1450 to a little younger, down to 1350. And these are present across multiple cratons, all the way from East Antarctica through Laurentia into Baltica and such. So there's a whole swath of these intrusions, and they're called A-type granites. Is another way to refer to these anorogenic granites. They all kind of share the characteristic that they're very coarse-grained granitic rocks. Of course, a granitic rock, felsic, big crystal, igneous rock. And so you can see these are mostly lighter colored grains. The darker material is probably less than 15% of these rocks. Coarse grained, meaning you can see the crystals and they're bigger than 5 millimeters or so and up to a few centimeters. But when they're really big and some of the crystals are bigger than a few centimeters, we call these megacrystic granites. And what's mega about them are these big alkali feldspar crystals, the big kind of peach colored crystals. And so very characteristic granite, very pretty granite, and in fact it's used commonly as a countertop. You might recognize it as such. In Arizona, we have a number of different examples of anorogenic granites in the Grand Canyon. In the western end, there's the Quartermaster Pluton down near Lake Mead. In the transition zone near Prescott, the Dells granite. These are massive rocks. They tend to be heavily jointed, and you can see the jointing in here, which makes it, and the erosion along these joints makes it a great place to boulder and climb. Farther south, in the Basin Range, in the Phoenix area, there's the Ak-Chin, Komatke granites in the South Mountains and Sierra Estrellas. And then the McDowell Mountains have granite as well, like this up near Troon, the golf course. Well, in the central part of Laurentia, there's what's called the Keweenawen supergroup, and this is an age of about 1100 million years. And it's thought that these rocks are rift related. So Rodinia had just started to assemble, but some parts of it were still unstable and it was trying to rift apart in a certain area. And actually this part of Laurentia was trying to rift apart on an axis right down from Great Lakes on an axis southwest towards West Texas. And so these rocks, except for in the Wisconsin and Michigan areas, are pretty much covered by younger rocks and they're in the subsurface. So what we know of these are from well logs and geophysical data. But it's a compilation of mafic volcanics, basalts, more or less, and basaltic or mafic intrusions like diabase, dikes and sills and things like that, combined with sedimentary rocks. And so this map shows in green where the volcanics are and in yellow where the sediments are. And the black lines are major faults. And so as it tried to rift apart, you had these faults and created little basins, and the sediments would be deposited in some of these basins. And as the rifting occurred, you had volcanism. So it's very common rift-related volcanism and sedimentation. Farther up into Canada, we don't see the volcanics, we see more of the intrusive part of it. And so these are the mafic dikes that are related to this rifting event. This is an area on Lake Superior where the rocks are actually exposed at the surface. Well, now in western Laurentia, we have another supergroup to talk about, and this is called the Grand Canyon supergroup. It has an age of about 1250, 1254 to be exact, all the way down to about 742. And it is on the same map. Bel Purcell was a little older, and then here's the Keweenawen. The Grand Canyon supergroup and related rocks are down here in the southwest. And these are mostly sediments and volcanics that were deposited on the continental margin and even in the shallow marine setting. Like I said, there's mafic volcanics, basaltic volcanics, and related intrusions, sills, and dikes. This is a strat column for the Grand Canyon supergroup, and it's interesting because it gives geologic time on the right, and then it shows the different rock formations included in the supergroup. This is all the supergroup right here. So the supergroup itself has two groups that we'll talk about: the older Unkar group and the younger Chuar group. And there's a couple other formations that aren't currently included in the two, the Nankoweap and the 60 Mile formation. So these are exposed in the Grand Canyon. And it's interesting with this diagram because it shows you on the geologic time scale where they fall. And this is the beginning of the Earth right here. And the oldest rocks in the Grand Canyon, the Yavapai supergroup rocks, the Vishnu schist and such, have an age right here. And there's a big time break between the Vishnu and the Grand Canyon supergroup. And that's what we call nonconformity, because the rocks right now are right next to each other. But really that boundary spans a whole lot of time, missing time. And so the older part of the supergroup was here, then there was another unconformity, and then the younger part of the supergroup is here. Okay? And then there was another break in time, and then finally the Paleozoic rocks came in over the top. And then after that, the Grand Canyon sequence ends. So it's an interesting diagram. Well, the Grand Canyon supergroup has two parts to it. The older Unkar group spans the range of 1254 down to 1104. And notice those aren't like even numbers. It's why isn't it 1250 or 1300? Well, it's because we have a date, specific date on a rock. And in this case, we have a recent date of 1254 on a volcanic ash right at the base of the group, which is a good place to date the first and oldest part of it. And then 1104 is a good radiometric age on the lavas right at the top. Good datable units and their positions in the stratigraphy give us these specific numbers. And so the Unkar group is made up of a number of smaller rock units we call formations. Okay, and so supergroup, group, formations, and then you can go further from there. So the oldest part of the Unkar group is the Bass Limestone or Bass Formation. That's the one that has the age of about 1254. It's good that volcanic ash is in there because most of this formation is sedimentary and you can't really get a date from it. But recently we found this volcanic ash and we're able to date that part of the unit. The Hakatai Shale is a very distinctive brick red, orangish red sedimentary unit right on top of the Bass Limestone. The Shinamo quartzite, love that name, Shinamo, is a massive sandstone which is very hard and very compact sandstone that was given the name quartzite. And it's kind of confusing. How can you have a shale and a sandstone with a quartzite in between? It really is a sandstone. We could have called it the Shinamo sandstone. But it's a very pure sandstone, and it's mostly quartz grains, cross bedding, stuff like that. Very resistant, very hard. Okay, and so it forms these cliffs right here. The dock sandstone above it is another thick sequence of sandstones and siltstones. So all sedimentary here. And then the top of the group is capped by cardanous basaltic lavas and related intrusions, diabase sills and dikes. And it's these that have an age of about 1104. Here's an example of one of the dikes of cardanous age, basically cutting through older rocks. And these older rocks are the reddish rocks of the Hakatai Shale. And this is at Hance Rapid. This is the Hakatai here, and this is actually the Shinamo above it. And so this is the cardanous, which is an intrusion that is cutting through the older Hakatai and then Shinamo. Unkar group. A little farther south from the Grand Canyon in central Arizona is the Apache group. And this has an age of about 1340 to about 1050. And these are, again, mostly continental sedimentary rocks, sandstones, mudstones, things like that. And so the Apache group itself is a combination of several formations: the Pioneer Shale, the Dripping Springs Quartzite, the Mezcal Limestone. Again, notice the mixture of sedimentary and metamorphic names. Don't worry about that. Basically, Dripping Springs Sandstone, the Mezcal Limestone, Pioneer Shale. So they're all sedimentary in origin. And then the Troy Quartzite is on top, and they haven't included that in the Apache group, but it's pretty much just the youngest part of this sequence. Also, what are very abundant in the sequence are sills, mafic sills, diabase sills that are about 1100 million years, so same age as the Cardanus in the Grand Canyon. And these are all exposed in the Salt River Canyon, which is a little secret canyon area of Arizona. If you take Highway 77 out of Globe up onto the Mogollon Rim, you'll pass through this area, and it's fantastic. And it's all Apache group rocks, with the Mezcal limestone and the diabase sills forming the canyon walls. The darker mafic sills and the lighter colored sedimentary rocks are pretty distinctive. The Sierra Ancha is a mountain range in this area too. A very rugged and remote wilderness area in central Arizona with a lot of Apache group rocks. And like I said, the diabase correlates real nice with similar rocks in the Unkar group in the Grand Canyon. And so it's thought the Apache group is more or less correlative with the Unkar group. So there are ore deposits of Mesoproterozoic age in Arizona, and there's a variety of different types that produce tungsten, uranium, asbestos, even magnetite, which is an iron ore. And so these are distributed across the central portion of the state in the transition zone from eastern Arizona and Gila County all the way across Yavapai County into Mojave County. And they're different deposits and they have different sizes, but one includes asbestos, and this is pictured here. This is a seam of asbestos in the Mezcal limestone, and you can see the fibers of asbestos, and this is called chrysotile. Asbestos is a family of different minerals, and like any family, you can have good family members and then you can have a few black sheep. And with asbestos, chrysotile is one of the good ones, and the bad one, which is the carcinogenic one, is not chrysotile. And so again, when you hear the word asbestos, everyone kind of freaks out. It's kind of gets a bad rap because as certain kinds like chrysotolite, which is the bad one, it's based on the mineral amphibole, is insoluble, and it's got a little hook in it, and basically if you breathe it in, it can get lodged in your lung and it doesn't dissolve, and that causes problems. Chrysotile is different. It will not interact with your lungs that way, and so it's totally different structure. So not all asbestos basically is evil, but the reason why that's there is the Mezcal limestone had all the ingredients to make it, and then right out of this picture here is a diabase sill, and the sill came in after the Mezcal. It's an intrusion, right? And heat from that intrusion drove fluid activity through the Mezcal limestone, and it rearranged the chemical composition in some of these fracture zones, and it took some of the elements out of the Mezcal and started to make asbestos. So we see, in this case, these little seams of asbestos here, and in some places they're economically valuable ore deposits. And finally, Mesoproterozoic life. Still not a whole lot to talk about, but we do have red algae, and so we get the first sexually reproducing organisms on the planet at about 1,200 million or so. And these are photosynthetic eukaryotes. That's great. And so this is what red algae looks like today, and it was probably a lot similar back then. A big step forward, though. It's reproducing in a sexual fashion, translating the DNA in a different way than just the binary fission process. Stromatolites are the same old, and they've been around a while. Not eukaryotic, prokaryotic, remember. They are photosynthetic, and they have different shapes and sizes from mats to mounds to domes to toadstools. But it's really in the Mesoproterozoic where they have their greatest abundance, and maybe as much as 60 times more than that you see today.